Welcome back to the Natural Hogarithm. What is this, and where does it even really come from? Well, today we're going to unpack complex numbers and not only discover one of the most profound formulas in math, but also one of the most intriguing and mysterious identities. E to the I pi equals -1. Let's begin. First, what is a complex number? That's pretty important to know if we're going to understand our identity, right? Well, complex numbers are built on the imaginary unit I, which is the square root of -1. In other words, I squared is equal to -1. What makes complex numbers important is the subtle geometry hidden within them. Consider a real value plotted on the number line. We'll call it a. If I multiply a by -1, I can plot -a on our number line. This looks like and is a 180-degree rotation of a on our number line. However, -1 is equivalent to multiplying by I twice, right? I squared is equal to -1. If multiplying by I twice rotates a by 180 degrees, multiplying by I only once should rotate by half of that, by 90 degrees. We can plot I times a up here, where it would logically land after rotating by 90 degrees. But it's not on our number line anymore, and we need a new complex plane to describe where these imaginary numbers even fit. This is the complex plane. It has two axes, one for real numbers in blue and one for imaginary numbers in green. With this new coordinate system, we can see where all numbers, real and imaginary, have to fit. But most importantly, we can see that multiplying something by I encodes a 90-degree rotation. That key principle is at the heart of e to the I pi equals -1. Mathematicians define complex numbers with the letter z. I see it a lot with this little line drawn through the middle, so I guess I'll follow in suit. Each complex number has a real part a, which I've drawn in blue, and an imaginary part b, which I've drawn in green. Complex numbers can be written as a plus bi, the real part plus the imaginary part. We can go ahead and graph these complex numbers on our complex plane. It's simply the intersection of these 2 points. Now, if we draw out the components of our complex number, we can see that it forms a right triangle. This is really the same technique we use on our unit circle when we're defining a point on there. I'm going to call this angle theta, and I'm also going to call our hypotenuse r. Now, there are 2 ways to define complex numbers in terms of this angle theta. One is trivial and one is definitely not. The first way is in terms of our triangle. The real part, a, is simply equal to r times the cosine of theta. And our imaginary part b is simply equal to r times the sine of theta. We get those from our right triangle. Now, the second way we define complex numbers is a lot more confusing. The equivalent yet really odd way is through z equals re to the I theta. Now, that expression might seem odd, and it should, but there is actually a hidden but beautiful geometry embedded within this expression. Let's prove that these are equivalent, because once we do, Euler's identity is really just one step away. The exponential function is so important because its derivative is itself, right? If I let f of t equal e to the t and take the derivative, well, f prime of t is also equal to e to the t. The rate of change of f is f itself. If we instead named a function g to be e to the 2t, well, when we go ahead and take the derivative, we're going to have to multiply by the derivative of the exponent by chain rule, and that would leave us with 2e to the 2t. It's not quite g of t as the derivative, but it's 2 times it. It's a scaled version. The fact that we're preserving g of t at all is what makes this function so important. What if I instead named a function s of t and let that constant in the exponent be I? Well, if I follow the pattern consistently, the derivative s prime of t would simply be I times e to the it. In other words, that's I times s of t. The derivative is simply multiplying s of t by I. What did we say earlier about I? Well, multiplying something by I translates to a 90-degree rotation. In other words, the rate of change of s is simply a 90-degree rotation of s. S prime of t and s of t are perpendicular to each other. Let's hop into an example and I'll show you guys why this relationship is so important. We can think of e to the it as some position function. I'll label this function s of t equals c times e to the it, where c is just some constant that we have the ability to change. It makes the function more general. From there, we can come up with a velocity function. Now remember, velocity is simply the derivative of position with respect to time. And so v of t is then equal to I times s of t. That's because of our derivative rules with e to the it. By the chain rule, we simply multiply by I out front. Awesome. Now if we represent this with vectors, with s of t and v of t being perpendicular to each other, a very specific type of motion pops out. Notice the velocity vector doesn't act in the direction of position at all, right? It's perpendicular. As time passes, the velocity vector only ever changes the direction of our position vector, and never its size. Well, what is that size of our position vector? Because the velocity can't change the actual length of our position vector, its initial size is its size for all times t. It can't change. The magnitude of our position is constant. At time t equals 0, s of 0 equals c, and so our position vector's size is set to a length of c, that constant out front, for all times t, and it cannot change. Similarly, our velocity vector can't change size, as its derivative, by the derivative rules of e to the it, would also be a 90-degree rotation of it. Acceleration is, in other words, perpendicular to velocity. Because v of 0 equals c, the size of our position and velocity vectors are both c, and they never change. This might not look like much, but this exact geometric constraint leads to uniform circular motion. I'll show you guys what I mean with a demo. Here we are, uniform circular motion. That position vector cannot change size, but because it is constantly changing direction, it acts like a radius, and in fact it is. This exact setup traces a circular path through space. Because e to the it traces a circle in the complex plane, we can reach any complex number we want, so long as we change the radius accordingly. And that is it. We have proved geometrically that e to the it is another way to represent a complex number. We now have two forms, c e to the it and r cosine theta plus I r sine theta. Both are perfectly valid ways to represent complex numbers. However, our last job is to connect the two ideas and reach Euler's identity. Here's c e to the it plotted on the complex plane. As we mentioned earlier, its size is equal to the constant c, and because it is a radius, that value of c will never change. However, to reconcile e to the it with our other definition of a complex number, we need to connect to the constants c and r, and the variables t and theta. Well, the easy connection is to see that c and r represent the same thing. It's that radius, or distance, a complex number is from the origin. By that logic, r is equal to c. Perfect. The trickier part is connecting t and theta. To do so, we need to ask what our velocity function, v of t, actually represents. If we let some time t pass, our position function will sweep an arc on the circle, tracing some arc length s. The velocity function tells us how fast we sweep that arc. In other words, the size of our velocity tells us how much arc length we trace per unit time. Now remember, we need to connect t with this angle theta that I just drew. If theta is in radians, then by the definition of a radian, the arc length we sweep is equal to the radius multiplied by theta. Theta tells us how many radii fit onto the arc, and multiplying by r makes that number into a distance. We can substitute this expression in for s, and we are almost done. Let's note two things. First, the position and velocity functions have the same size, and because the position function size is equal to r, the velocity function size is also equal to r. We can plug that into the expression and see that r cancels from both sides, leaving us with theta is equal to t. There you go. That is exactly what we were after, and we can go ahead and plug that back in. We now have two expressions for a complex number, both in terms of a radius r and an angle theta. Because they equivalently represent the same thing, we can set them equal to each other. The constant r is common in every term, so we can cancel it out. We are left with the following expression: e to the I theta equals cosine of theta plus I times the sine of theta. This is Euler's formula, one of the craziest equations in all of math. It is pivotal in fields like quantum mechanics, complex analysis, signal computing, and differential equations. Euler's identity, what we have been after this whole time, is a simple case where this angle theta is equal to pi radians. Rotating pi radians around the circle lands us at the complex number z equals -1 plus 0I. Because we landed on the real number line, our answer has no complex component, and is simply equal to -1. Therefore, e to the I pi is equal to -1. We can also plug pi in for theta in Euler's formula and arrive at the same result. E to the I pi is equal to cosine of pi plus I times the sine of pi. The sine of pi is equal to 0, and cosine of pi is equal to -1. We get the same result. E to the I pi is equal to -1. No matter which path you take, Euler's magical identity just pops out. There we have it. We're done. I hope you enjoyed this video and built an appreciation for Euler's identity beyond the math gimmick that I feel like it is. Beneath all the symbols is a really beautiful geometric relationship that builds one of the greatest formulas in all of mathematics. I've been the Natural Hogarithm. Have a great day, and keep learning.